Hey guys, I got one more type of problem for you guys, so let's go ahead and get to it really quick. Okay, so this is called example 3, making a box. And actually, why don't you guys go ahead and write this down? So you can pause this really quick. It's an open box is made by cutting congruent squares of side length x from the corners of a 20 by 25 inch sheet of tin and what does that say? Tin and bending up the sides. Sorry about that. So that's bending up the sides. How large, how large should the squares be to make the box hold as much as possible? What is the resultant max volume? Okay, so basically that last question is how large should the squares be to make the box hold as much as possible? And then what is the max volume? Let me kind of demonstrate what it is that we're looking at. It's an open box by concurring square sides of side length. So there should be a rectangle with side lengths of 20 by 25. But then we have some weird artifacts here by cutting up squares of side length x from the corners of this 20 by 25 inch sheet of tin. So what I've drawn here, or what I've kind of made, let's see if I can kind of get this in the frame here. Let's get out everything else except my wonderful drawing. Okay, so pretend that this was a tin sheet of metal, right? And this length was about 25, what was the unit? Feet or so? 25 inches, right? 25 inches. It's not really, but let's just say it's 25 inches, right? Straight across. And then down here is 20. So this is 25. I'm sorry. So this length would be 25 inches. This is about 20. Let's go back to the problem and see what it's asking. Again, it says we have to cut congruent squares of side length x from the corners of the 20 by 25 inch sheet of tin. So I cut in by each corner a square with the same side lengths. So I don't know what the side lengths are, but they're the same side lengths, and I cut them off at the tips here. Okay, at the corner, at the corner, at the corner, and at this corner here. Let me get out that weird prompt bubble back here, down here, okay? The whole point of this is if I flip it upside down and I cut up the squares, I can bend up the tops. The only thing is I'm missing like a cap, right? If you guys can kind of see, maybe it's a little bit easier to understand from the side, but do you guys see this? In 3D, in 3D, this should give me, I even called it 5.4 example 3, making a box. You can find this in example 3 in your book, making a box in 3D shape. See, so we're trying to maximize the x values to which we could do this. Like, what's the highest x values that I can get away with to hold in as much as I can in this box? So the only thing is this box does not have like a cap to kind of cap this off, okay? But we need to maximize the volume of this cube, okay? So let's think about what we just looked at. Sorry, I'm going to get a piece of paper here. Ooh, no, sorry. Behind the scenes, I'm fumbling all over. I'm losing it, guys. I'm sorry. I'm super losing it right now. Okay. So let's think about the box, the dimensions. So let's think about this really quick. The height of the box. Or actually, let's think about the length and the width of the box. The length I would consider is the wider point, or the wider, or the longer. I'm sorry, the longer of the two. So the length of the box was 25 inches. But if we think about it, we have to consider now the new length, because we're going to bend these guys up here the new length was 25, but we have to take off certain amounts that we cut off, or certain amount of length that we cut off. We cut off this x length and then this x length in order to bend this. So the new box is actually 25 minus 1x and minus another x. So that's 25 minus 2x. Same case goes for the width, which is a little shorter. It used to be 20 across, but then in order to bend this up from both sides, we had to cut off the length. So here it was originally. So if you think about it, it's more actually at this top right here. It used to be 20 inches across. Same goes for when we're talking about the length back on this side. But we're talking about the width. It used to be 20 inches across, but we cut off an x length here and an x length here. So the width now, which used to be a full 20, is now just 20 minus 2 of those x's. So it's 20 minus 2 of those x's inches, if you're wondering. And the height of the box, if you think about it, the box sits up like this, right? Oh, sorry. Let's see if I can kind of get this off. I think you guys kind of get the idea. The box height, you can kind of tell from the side, is x height long. Okay? And we're trying to maximize the volume. So really, that's the function that we're looking at, or the equation is the volume. So put all these pieces together. So it's length times width times height, in which we have, that would be, so f of x is the volume that we're looking for. Or I think in your book, it might actually switch the f and just say the volume, which is a function of x, is 25 minus 2x. That's the length. The width is 20 minus 2x times x. Okay, so let's see. Anything else here? Okay, and one other thing too that we have to consider is, let me see. One other thing that we do have to consider is the domain here, because this is a real tangible box, right? So if we get numbers that are below, because we might actually get maximum minimum values, because remember, if we plug this into a graph, right, it might be a continuous graph that goes forever. I don't know, right? It can go from x values, right, x values that are positive to negative. But we do want a domain, and we want actual real numbers here, okay? Meaning, can I actually have an x height, if you think about it, that's inches, that are negative? No, this is real life. They have to be positive numbers, okay? Unless we're talking about antimatters, on which I can't get into because I don't even know anything about it and how this relates to a simple problem like this. So we can't have values that are less than 0. So the domain, we have to just keep in mind that if we find out maximum minimum values, they have to be from 0 to, let's see, what else can we also do? We can actually set these and see what values give me 0 here. I'm going to set up 25 minus 2x and set that equal to 0. 2x equals 25 divided by 2. I think x could have a limit of 12.5. Okay, shouldn't exceed 12.5. Or else if I put in anything bigger than 12.5, I get a negative number in here, which makes this whole volume negative. That's not possible. But I think the limiting factor will be this right here. 20 minus 2x, you set that equal to 0. You solve for x. You get 2x is equal to 20, and then you divide both sides by 2. Sorry to do this kind of weird work, but then you have x equals 10. So you don't want to exceed anything above 10, because if I plug in anything bigger than 10 for x here, this makes this parentheses, this parenthetical value, negative, which makes the whole volume negative. So again, this is a graph that has no limitations at this point right now. Mainly because it's just a function. It's just a function that we can plug in. We can technically plug in negative numbers if we want, but in our situation, since we're making a real life tangible box, they have to be within parameters that make a volume that is positive. It doesn't dip below the graph. And also, because that wouldn't make sense, then you'd have negative volume values, and you can't have x values that make the height, the width, and the length negative either. Okay, so we're looking at a domain that has to be 0. Sorry, so I'm continuing off from what I wrote here. 0 between 0 and 10. Okay, so just keep that in mind. Right? Okay. So let's see math here. Okay, so my recommendation is just to multiply this whole thing out. So we'd have to do sort of like FOIL, and then what I'm going to do is I'm going to FOIL 25 minus 2x times 20 minus 2x times x at the end, okay, just to make it easy, because I think that x kind of throws in a little bit of that complication there that I don't want. So 25 times 20 would be 400 or 500, I believe. Yes, it's 500. Then I do outside. 25 minus 2x is minus 50x. Inside is minus 40x. And then the last part is minus 2x times minus 2x. That's plus 4x squared. So let's rearrange this in a way where I like having the numbers that have a variable with the highest exponent first. Okay, the order of magnitudes, or not the order of magnitudes, but it's just that's generally the order that we like to classically put. And sorry, that's minus 40x right here. So let's see, that is minus 90x plus 500 times x, which would just be 4x cubed minus 90x squared plus 500 is, so this is still just the volume. If you know how to find the maximum minimum values here, step 1 is to find the derivative, the first derivative of this guy. So if I found the first derivative, it'd be pretty simple. It's 12x squared minus, bring down the 2 times 90, and you subtract 1 from the exponent, that's 180x, and let's see. Oh, and I forgot to say, when we distribute that x into all the guys in here, that's 500x. It's plus 500. Okay. So you have two options, right? In order to solve for the second step, which is finding the roots, you're probably not going to want to hear this. I'm sorry to say this, but you might have to do the quadratic formula to find this, because it's really hard to do this by hand algebraically. If you want to do it by hand, you have to do this good old trusty quadratic formula, which can solve for any roots, for any quadratic equations. A quadratic equation is anything with an x squared, or x to the second power is the highest x exponential to an x to the variable x power, with a polynomial that has 3 terms. So that's a quadratic equation. How to solve quadratic equations, you would use the quadratic formula. That's one technique, but that's probably, I think, the best technique by hand that you can apply. You don't have to do completing the square, you don't have to do all the other stuff. Okay, which I know because I'm like the integrated math 2 teacher here, so I would know how to do that. Okay, so we could do this by hand, so we can just do that. Let's just do that really quick. Negative b, so this is my a, this is my b, and this is my c. My b is 180, it's the number in front of the x, so that's negative 100, negative 180, so negative 180 plus or minus the square root of negative 180 squared minus 4 times 12 times 500. You're going to love this. Over 2a, 2 times 12. So I believe that is 180 plus or minus the square root, which I'm not even going to do. I'm just going to say that's 180 squared minus 48 times 500 all over 24. So if you do this in the calculator, so I'm not gonna lie, I'm just gonna say I did this by a calculator, okay, to save some time. I got 2 possible answers. So remember, one of the answers is 180 plus whatever's in here divided by 24, and the other answer is 180 minus whatever's in that square root sign over 24. You should have gotten about 11.317 and 3.681. Okay. Now the other technique that you could have done is you could have actually graph this on your graphing calculator. $12x squared minus 180x plus 500. So let's get up the graphing calculator really quick. Okay, let's see. All right. Clear that. Let's go here. Let's clear that. Let's put 12x squared minus 180 squared, or x, I'm sorry, plus 500. You're gonna love the way this looks. Okie dokie. That's not gonna be easy. So let's zoom out a little bit. Okay, and I know that's a quadratic formula just going all the way down there. Okay, and I could change the window, but I really don't have the time to do that. So then I would do second trace this button, go to down to 0, and then I could try to find the x. It's gonna be kind of hard because I don't see where's my arrow. Okay, so you guys see that arrow or that little cursor? All right, right there. So I could say left bound of this 0. This is so this point is technically a little bit to the left of this point here. I'll press that. Yes, right bound is you want to go to the right. So you got to trust that the cursor just went up. It's to the right of this x-intercept. Guess you press 0. So that's 11.3. So which is exactly what I got here. Whoa. Which is exactly what I got here, 11.318. So there's just 8 minus 317. And then you do the same thing for this guy, for this point over here, and then you get 3.681. So you have two options. You can graph it, or you can do it by hand here, okay? The next step is to do that number line. So I'll probably continue on another page. Oh, sorry, that's not 0, but that's a 3.681. You want to put down your two values here. This is 11.317. Sorry, I did write it in a weird way, this number line, because remember, now let's include the domain. If you remember back to the domain, had to be within 0 and 10, or else this box really wouldn't exist. And if you think about it, that only gives us two options. Let's include the domain. This can't be a value. So even though that could be a max value or a minimum value, which we don't know yet because we haven't tested it yet, we know that can't be the number because that is a number that exceeds our limit or our domain. Because we've determined before that whatever the max or minimum value for x is, it has to be between 0 and 10. And that number is maybe a maximum or minimum value, but it exceeds our limit, which would give us negative values for our, if you remember back here, or just it would make it so this would be a negative volume, or just reiterating one more time, if I plugged in 11.17 or 317, namely in here, the width would be negative. If you think about it, 20 times 2 times 11, that'd be like 20 times minus 22. That'd be like a negative value. That would not make sense. And if I plug that back into here, that for one, I would have a negative width, and also my volume would be negative. That makes no sense. If I plugged in that negative number in here and multiply it to whatever here, that's insanity. That doesn't work, okay? So let's just test to see if this is indeed a minimum or maximum value. I'm hoping it's the max. Is it the local max? I don't know. So very easy. Let's take a point. I'll say f, or the v prime of 1, which should be, if I remember back, what was the equation? It was 12 times 1 squared minus 180 times 1 plus 500. That'd be 12 minus 180 plus 500. I think if I did that sequentially, it'd be like minus 168 plus 500. Not quite sure what that is. Was it like maybe 332? Did I do that right? I don't know if I did or didn't, but that's positive. That's a resounding positive. So all these slopes are going to be positive. And on this end, we're going to try 3.681 to any number above here, but namely, let's just do a number maybe that's close to this, 4, and it'd be like v prime of 4 would be 12 times 4 squared minus 180 plus 500. Let's see here. First derivative. Oh, it's 180 times x. That's what I did. Sorry, guys. That's 180 times 4. So 12. That's so 12 times 16 minus 180 times 4. That's what I did wrong. Sorry, I was looking at my math here. And that'd give me, I'm not sure what 12 times 16 is. Let me just do that by hand really quick. That'd be 192. And 180, that's minus, I think that's, let me see. That's minus 720 plus 500. Let's add the 100, so that'd be 192 plus 500. That'd give me about 692. The positive numbers I'm combining minus 720. I think that'd give me 28. Negative. So this is telling me that these are all going to be negative slopes. And if we remember anything with, so at 3.681, right? We have positive slopes. And then from here, we have a bunch of negative slopes. That's a max right there. So yes, thank you. That would be 3.681. And I think, what did the question ask me? So you don't have to have any of this stuff here, is a local max. Okay, so really, the only things I need to show you were this and the signs here, and then reiteration of the domain. I think is, what is the resultant max volume? So if we know that 3.681 is the biggest value for x, we know that the height, let's go back, the height was x, so that's 3.681. The width was 25 minus x, which is going to be, or 2x, which is 25 times, or sorry, 25 minus 2 times 3.681. And then the length would be 20 minus 2x, 20 times 2 times 3.681. And you can plug it in. I'm not really sure what that would give me. Okay, if I plug this in. So I can multiply the height times the width times the length, all these three to get the volume. Or I have one more option. Okay, I could just go back to the original volume equation that I simplified down to, which is 4 times x to the third power minus 90x squared plus 500, which stems from the same thing. 25 minus 2x times 20 minus 2x times x. But the volume right there is just that. So I have two options. I could just find out the width, the height, the width, the length individually, and then multiply them together. Or I could use that 40 times 3.681 cubed, I think, minus 90x, minus 90 times 3.681. What is it? Plus 500x plus 500 times 3.681. Okay, and that should give me the max volume, whatever that is. Let's just do that really quick. I think I have enough time to do that. So let's quit out of here. 40 times 3.681. I'm going to do the caret sign. Cubed. Minus 90 times that. Minus 90. You guys are probably a lot quicker than this at me. 3.681, unless you're just kind of passively watching and seeing. Oh, is that? Sorry. x squared, so I should go back in my work. I'm making a lot of mistakes here. Right here, that is 3.681 squared plus 500 times 3.681. It's going to be a lovely number. Ooh, look at that. So I got about, hopefully that's what the book says. I'm not really sure what the book is saying, but 0.9. And what's the unit there should be inches cubed, because we're doing a dimension of height, width, and length. Each are within inches. And if you do inches times inches times inches, that's inches cubed. So you should have got about 2,616 inches cubed. All right, guys, that's it. Thank you guys for watching. You guys have a great day. Bye.